All right, hello everyone. So we're going to continue with chapter 21, material which is entitled Alpha Carbon Chemistry, Enols and Enolates. This actually really naturally picks up off of the last two chapters that we studied. First was aldehydes and ketones, and then carboxylic acid derivatives. Um, and so, what the heck is an alpha carbon, right? When we're talking about alpha carbon chemistry, we're talking about the carbon that's located one away from a carbonyl carbon, right? So if you have an aldehyde, a ketone, or a carboxylic acid derivative, those are all, um, they all share these carbonyl groups. We talked a lot about carbonyl carbon chemistry, how that can be considered an electrophilic site. Now we're going to talk about the carbon one removed, okay, the alpha carbons. What's so interesting about these alpha carbons is not actually the alpha carbons, but the alpha hydrogens, right? So the hydrogens that are bound to that alpha carbon. These alpha hydrogens are considered relatively acidic, okay? So a lot of, every single one of the reactions that we're going to see is all about removing one of these relatively acidic alpha hydrogens. And then you're left with what's called an enolate ion. We'll see that in a second. But yeah, that's going to be the main sort of theme of this chapter here. So looking at the pKa's of these alpha hydrogens, right? pKa, remember, is a measure of just how acidic a hydrogen is, how easy it is to remove a hydrogen. The lower the pKa, the more acidic the proton, right? So just sort of eyeballing, looking at these here. First of all, right, so we have an amide. This is an ester. This is now a ketone. And this is an aldehyde. You see that the pKa's are, sort of 30, 20, 25, 17. Those are not absurdly acidic by any means, right? For comparison, something like HCl, a strong acid, the pKa there is around -7. Water, something that we don't really consider to be an acid, but we know we can readily or rather we've seen many cases where it does donate a proton, has a pKa of around 16, right? So these are all even more, for the most part on this list, even higher than that. Nonetheless, they're still going to be able to be removed by a strong base. Okay, so in all of these, you're going to see that you're going to need a strong base. Obviously, if you have an amide, you're going to need an even stronger base than if you have an aldehyde. So first of all, notice these trends here just with respect to the different carboxylic acid derivatives that we talked about, the amide and the ester, as well as the ketone and the aldehyde. The aldehyde is the most acidic alpha hydrogen, the amide the least. If we go now to these, like what would be called like a 1,3 dioxo, basically when you have two carbonyl groups separated by exactly one carbon, that will decrease the pKa quite significantly, right? So this is now, just to clean up here, this is now a diester, right? So if we're going to compare the pKa of an ester to that of a diester, and again, specifically a diester that's located 1, 2, 3 carbons apart, that alpha hydrogen in the middle there, it's that much more stabilized, right? So anytime you have two carbonyl groups separated by just one carbon, that hydrogen in between those groups are significantly more acidic. So then if we get all the way down here to this, it's actually like an aldehyde on one side and a ketone on the other side. That's pKa is around 5. So now you're getting sort of in the range of like a carboxylic acid or something like that, something that is very readily donatable. Okay. Just, the take home message here, one being the trends that we see of increasing pKa among these groups that we've learned. And then also, if you have these 1,3, sort of what could be broadly called a 1,3 dioxo. Remember, oxo is the name of those. Is another name for the carbonyl group, right? So located 1 and 3 carbons apart. Those are going to be, that adds like will drop your pKa no matter what the functional group you're talking about, carboxylic acid derivative you're talking about. If it's a 1,3 dioxo, you can sort of bet that the pKa is going to be quite a bit lower. Okay, so like we we're saying, these are we are going to consider these to be relatively acidic hydrogens. We're going to keep on putting that little qualifier relatively in there, so we don't think that we're talking about a strong acid or even a weak acid, really. Rather, something that can be removed by a strong base. So because of that, we need to be sort of strategic about the base that we choose, right? So first of all, remember, how do we determine the way an equilibrium, like which direction an equilibrium favors with an acid-base reaction? You look at the pKa of, in this case, the acid, which would be the ketone, and the pKa of the conjugate acid. So that's what happens when you protonate your base. And the equilibrium will always lie in favor of the weaker acid, in favor of the formation of the weaker acid. So whichever side has the highest pKa, that's where that reaction is going to point to. So you see that you can't use an alkoxide ion with this ketone and readily create, again, this is what we call an enolate ion, because the this reaction favors the reactants. It doesn't favor the formation of the products, and those pKa's are pretty similar. So it'd be like, a 90-10 or something like that. But still, you're not going to be able to readily create a large amount of enolate using this particular base. Because of that, there are two really strong bases that are commonly chosen. Okay, first of all would be sodium hydride. This is one that we've sort of talked about before, especially in the context of removing a hydrogen or deprotonating an alcohol group, right? So to create an alkoxide ion, these are like the base of choice. So this is a great base to choose. That this will sort of readily push things into the product side. The other one, which is going to be new to us, is what's called LDA. This is another strong base. It's got so LDA, lithium diapropylamide. It's basically very similar to an amide ion, except it's got these big bulky R groups on there. It is sort of the base of choice for deprotonating our alpha carbons. Why do we want that instead of just using the amide ion? Well, the amide ion is also a good nucleophile, right? So by putting these big bulky groups on there, we sort of eliminate any sort of nucleophilic attack and ensure there's just the base attack of the proton transfer, having it act as a base. So I mean, just so we can all make so note that the pKa of the conjugate acid is going to be 36 compared to the pKa of our alpha hydrogen. So this is a reaction that will really fix. Hopefully we all have reaction mechanisms of acids and bases down, but just to sort of go through that, the nitrogen, sort of amide ion, will do the attacking, grabbing that hydrogen, and that pair of electrons will remain on that alpha carbon. And again, we call this an enolate ion. Okay. If you're using one of those 1,3-dioxos, because those pKa's are so significantly low, you don't have to use quite as strong of a base, right? So we could use an alkoxide in this case. Why are those so much more? Why are those hydrogens so much more acidic? Well, remember that what makes a good acid is a stable conjugate base. And in this case, the enolate ion that's formed, that negative charge can be stabilized not only over the one oxygen, but also over the second oxygen as well, right? So that enolate ion that's formed is just that much more stable. So in this case, we really wouldn't need as strong of a base to use the LDA or the sodium hydride. We could just use something like an alkoxide ion in order to sort of readily create our enolate ion. Okay. Yeah, I mean, so this is just a summary slide, right? So if you take a regular ketone and you were to use something like sodium hydroxide or an alkoxide ion, you would end up getting this equilibrium. If you use something stronger like sodium hydride or LDA, then you'll get this 100% product formation as the enolate. Whereas if we have this 1,3-dioxo, we can just use sodium hydroxide or an alkoxide, and that gives us 100% population of the enolate. You wouldn't need to use LDA. Now, students will be like, well, couldn't I use LDA? Well, of course you can. The whole idea here is now factoring in the practicality of it. And LDA is going to be way more expensive. Sodium hydride is going to be way more expensive than sodium hydroxide. So if you can get away with using sodium hydroxide, you're going to. Okay, so there's actually sort of two reactive species we're going to see here with regard to alpha carbon chemistry. One, we just talked a lot about the enolate ion. This is actually the resonance form, and we'll sort of see this in a second, but this is another way of drawing that same thing. These two structures are in resonance with one another. This is going to be the dominant, the enolate ion is going to be sort of the dominant one that we see in our reaction mechanisms. That again is formed under the presence of a strong base. However, there are going to be alpha carbon chemistry that we're going to see in the presence of acid, and that forms an enol. We all remember enols because that's when we were introduced to tautomerization, right? An enol is just a double bond next to an alcohol group. You're going to see these formed as well in some of our reactions. And the bottom line here is that this carbon is still going, we're going to see that this carbon has still got sort of a little bit of electron density to it. So it's still going to be acting as a nucleophile, just like we'll see in our enolates. Main focus for this lecture right now is not going to be any sort of reactions, but just the mechanisms for how these form. Okay. Again, we sort of learned about enols in the context of tautomerizations and how we had these reactions that would form enols, but because of the equilibrium of tautomerizations, they would quickly tautomerize into the ketone form. Okay, so the ketone form, generally speaking, is the one that's favored at equilibrium. There are some exceptions. So for when you have a 1,3-dioxo, this is going to favor the enol a little bit more because there's like this stabilization between hydrogen bonding of the neighboring oxygen. So that helps stabilize it. So that pushes this reaction in favor of the products a little bit. And the one that's like 100% in favor of the enol form is when that enol is phenol, right? So if this is phenol, phenol, that's a very, very stable enol. And so in the case of this particular tautomerization, that favors the product side or the enol side quite a bit. All right, so how do we get from ketone to enol? First, under acidic conditions, right? So what do we think the first step is going to be when we have a ketone under acidic conditions? Same as always, you're going to first protonate that carbonyl oxygen. This carbonyl oxygen that's protonated is actually resonance stabilized, sort of a resonance stabilized cation where the positive charge moves between the oxygen and the carbon. Now, this is the more favored resonance structure because in this particular structure, everybody has a complete octet, right? Carbocations, that means that the carbon wouldn't have a complete octet. Nonetheless, it's actually the other resonance structure that's going to be very important for the enol formation. And that is you have water coming and grabbing that hydrogen, and that pair of electrons comes back down, forming your enol. Right, so this is this acid catalyzed ketone to enol tautomerization. Okay, base catalyzed. So again, this could be either acid or base catalyzed. Typically, under basic conditions, we won't see the enol playing a major role. It'll be that enolate ion, but nonetheless, let's make sure that we know how to do these mechanisms. The first step here is going to be the removal of that hydrogen, forming first an enolate ion, and then through resonance, that negative charge can bounce up onto the oxygen. that oxygen can then receive a proton and form the enol. Again, under basic conditions, it's actually going to be this guy that plays the dominant role in our reaction mechanisms. But nonetheless, we can draw this tautomerization under acidic or basic conditions. Okay, and then the whole shtick of the enol, just like the enolate, right? So if I would draw my enolate ion, it's pretty obvious that this carbon has a large amount of electron density and thus can play the role of a nucleophile. With the enol, it's a little bit harder to see, but if we draw the resonance structure for the enol, we again see that that one carbon, that alpha carbon, is left with a good bit of electron density, right? So that's why the alpha carbon in an enol is nucleophilic. And then lastly, again, really under basic conditions, the mechanism that's going to be really important that we're going to see over and over again is just the base removing. Remember, this is this alpha hydrogen, which we say is relatively acidic. So a base can remove that, and that's going to create this enolate ion where that carbon, that alpha carbon, has a lot of electron density and is thus a good nucleophile. Now, a lot of people will say, well, you have this oxygen that also has a lot of electron density, right? It just sort of depends on which resonance structure I draw. So there's sort of two different things that we could see in terms of our enolate ion under acting as a nucleophile, and that's either oxygen acting as a nucleophile or that alpha carbon acting as a nucleophile. It turns out that this carbon acting as a nucleophile is what we're going to see over and over again. We're not going to see this oxygen acting as a nucleophile. I don't even have a great reason for why that is, other than that's just not what's going on here. Okay, so although it's kind of weird because this is certainly the more stable resonance contributor because the negative charge is sequestered onto the more electronegative atom. Nonetheless, this carbon attack is what we're going to see over and over again. That's why the chapter is called Alpha Carbon Chemistry. Okay, and so this can be the case. So basically, whichever resonance structure you use, whether we're going to choose the enolate ion or we're going to choose this form of the enolate ion, they're both the enolate ion. We just got to make sure that the chemistry always happens at that alpha carbon, right? So even if I'm going to start with this one here, I'm going to have my double bond then playing the role of the nucleophile and that pair of electrons coming down to satisfy the octet of that other of the carbonyl carbon. The easier one, and the one you're going to see over and over again, generally textbooks like here, because again, it's the more stable resonance contributor, but chemists themselves are relatively lazy. And so the more common one you'll see is this red resonance structure, because then you just only have to draw one arrow, so it's easier.